why the laws of physics are not laws, let me tell you something that most physicists won't say out loud, something that would get you strange looks at a physics conference if you said it too bluntly. The laws of physics are not laws. They're not commandments handed down from some cosmic authority. They're not eternal truths carved into the fabric of reality. They're not even rules in any meaningful sense of the word. And I know this sounds like I'm being provocative for the sake of it. I know it sounds like I'm playing games with language, but I'm not. I'm being precise, more precise than most physics textbooks are willing to be. And after 50 years of working with these so-called laws, of using them, testing them, pushing them to their limits, I've come to a conclusion that I think every honest physicist eventually reaches. We don't know what the laws of physics are. We know what they look like. We know what they predict. We know they work spectacularly well in certain domains, but we don't know what they are. And the difference between those two things is enormous. Let me start with what most people think when they hear the phrase laws of physics. They think of Newton's laws of motion. They think of gravity. They think of conservation of energy. They think of Maxwell's equations governing electromagnetism. They think of Einstein's field equations describing how mass curves space-time. They think of Schrödinger's equation governing quantum mechanics. And they think these are like laws in the legal sense, rules that the universe must obey, inviolable, permanent, absolute. The universe does this. The universe never does that. End of story. Here's the problem. Every single law of physics we've ever discovered has turned out to be wrong. Not approximately wrong, not slightly off wrong. Replaced by something deeper, something more accurate, something that reveals the previous law was just an approximation, a shadow on the wall. Newton's law of gravity, perhaps the most celebrated law in all of science, the law that predicted planetary orbits and allowed us to send spacecraft to the moon, is wrong. It's been wrong since 1915, when Einstein showed that gravity is not a force at all. It's the curvature of space-time caused by the presence of mass and energy. Newton's equations still work beautifully for everyday situations. They get you to the moon and back, but they fail catastrophically near black holes at high speeds in strong gravitational fields. The law was never a law. It was an approximation that happened to work in the regime we could observe at the time. Newton's laws of motion, F equals ma, the foundation of classical mechanics. Every engineering student learns them, every bridge, every building, every airplane is designed using them, and they're wrong. They break down at speeds approaching the speed of light, where special relativity takes over. They break down at atomic scales, where quantum mechanics rules. They break down in strong gravitational fields. These so-called laws govern a tiny slice of reality, the slice where things are slow, big, and not too heavy. Outside that slice, they're useless. Maxwell's equations, the gorgeous mathematical framework unifying electricity and magnetism, 4 equations that describe every electromagnetic phenomenon from radio waves to gamma rays. Wrong, or rather incomplete. They don't account for quantum effects. They can't describe the photoelectric effect. They can't explain why atoms are stable. They had to be replaced by quantum electrodynamics, QED, which is a fundamentally different kind of theory. And here's what's really unsettling. QED itself, our best theory of how light interacts with matter, the most precisely tested theory in all of science, accurate to 12 decimal places, even QED is almost certainly wrong. It breaks down at very high energies. It can't be the final word because it doesn't include gravity. It's another approximation, a spectacularly good approximation, but an approximation nonetheless. Do you see the pattern? Every law we've ever found has been an approximation to something deeper. Every law has a domain of validity, a range of conditions where it works, and outside that range it fails. The law isn't really a law. It's a description that works here but not there. Now, but maybe not forever. For this but not for that. This should bother you, it bothers me. Because if every law we've ever discovered has turned out to be an approximation, what makes us think the laws we have now are any different? What makes us think that general relativity is the final word on gravity? What makes us think the standard model of particle physics is the ultimate description of matter? What makes us think quantum mechanics itself is the final framework? Nothing makes us think that. In fact, we have very good reasons to think our current laws are also approximations. General relativity and quantum mechanics, the 2 pillars of modern physics, are fundamentally incompatible with each other. They use different mathematical frameworks. They make different assumptions about the nature of space and time. They contradict each other in extreme situations like the center of black holes or the first moments of the Big Bang. At least one of them, probably both, must be replaced by something deeper, something we haven't found yet, something that might look nothing like what we have now. So when someone says the laws of physics, what they really mean is our current best approximations to whatever the actual structure of reality is. And we have no guarantee that those approximations are close to the truth. They might be, they might not be. We have no way of knowing. Let me push this further because it gets even more disturbing. There's a deep philosophical question lurking here that most physicists avoid. Are there laws of physics at all? I don't mean do our current equations work. They clearly do. I mean, is there an actual set of rules governing how the universe behaves? Is there a cosmic rule book? Or is that just a metaphor we've invented to make ourselves feel better about the patterns we've found? Think about what a law actually requires. A law requires an enforcer. Legal laws require courts, police, governments. Without enforcement, laws are just suggestions. So who enforces the laws of physics? What mechanism ensures that electrons always have the same charge? What mechanism ensures that the speed of light is always the same? What makes the universe obey these patterns? The honest answer is we don't know. We observe regularities in nature. We describe those regularities with mathematical equations. We call those equations laws, but we have no idea why those regularities exist. We have no idea why the universe is orderly rather than chaotic. We have no idea why mathematics works at all as a description of physical reality. Eugene Wigner, one of the great physicists of the 20th century, wrote a famous essay about this called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. His point was that there's no obvious reason why abstract mathematical structures invented by human minds should describe the physical universe so accurately. It works, but we don't know why it works. And that should make us humble about what we mean when we say law. Now, let me tell you about something that makes this problem even deeper: the constants of nature. Every law of physics involves constants, numbers that appear in the equations and determine how strong the forces are, how heavy the particles are, how fast light travels. The speed of light, the gravitational constant, Planck's constant, the charge of the electron, the mass of the proton, the fine structure constant. There are about 25 of these fundamental constants in the standard model of particle physics. And here's the disturbing thing. We have no idea why they have the values they do. None. Zero. No theory predicts them. No deeper principle explains them. We just measure them and plug them into our equations. The fine structure constant, which governs the strength of the electromagnetic force, is approximately 1 over 137. Why? Nobody knows. If it were 1 over 100, atoms would be unstable. Chemistry would be impossible. Life could not exist. If it were 1 over 200, the universe would look completely different. Stars would burn differently. The periodic table would be rearranged. Again, no life as we know it. The cosmological constant, which governs the expansion rate of the universe, is extraordinarily small, about 10 to the minus 122 in natural units. This is the most finely tuned number in all of physics. If it were even slightly larger, the universe would have expanded too fast for galaxies to form. If it were slightly negative, the universe would have collapsed long ago. It has to be almost exactly zero, but not quite zero. And we have no explanation for why it has this value. So the laws of physics aren't just approximations. They also contain numbers. We can't explain numbers that appear arbitrary, numbers that could in principle be different. This is not what you'd expect from fundamental laws of nature. Fundamental laws should be necessary. They should be the only possible laws. They should follow from some deep logical or mathematical principle. Instead, they look contingent. They look like they could have been different. They look, and I'm going to say something controversial here, like they were chosen not by anyone, not by some cosmic designer, but in the sense that they appear to be one possibility among many. And this is where I need to talk about the landscape, the string theory landscape. I've been involved in this idea for decades, and it's one of the most controversial ideas in modern physics. String theory, which is our best candidate for a theory that unifies gravity with quantum mechanics, doesn't predict a unique set of physical laws. It predicts an astronomically large number of possible sets of laws, something like 10 to the 500th different possibilities. Each possibility corresponds to a different universe with different physical constants, different particle masses, different force strengths, maybe even different numbers of dimensions. In most of these possible universes, the constants are wrong for life, wrong for complexity, wrong for anything interesting to happen. Stars don't form. Atoms aren't stable. chemistry doesn't work. But in a tiny fraction of them, an incredibly tiny fraction, the constants happen to be compatible with complexity, with chemistry, with biology, with us. If this picture is correct, and I think it might be, then the laws of physics in our universe aren't laws at all in the traditional sense. They're accidents, local conditions, the particular set of constants that happen to emerge in our pocket of a vast multiverse. Just as the temperature on Earth isn't a law of nature, but a local condition determined by our distance from the sun and the composition of our atmosphere, the laws of physics might be local. Conditions determined by which vacuum state our region of the multiverse settled into. This is deeply unsettling to many physicists. They want the laws to be unique. They want there to be one set of equations that describes everything that couldn't have been otherwise, that is logically necessary. I understand that desire. I felt it myself for decades. But the evidence, such as it is, points in the other direction. The laws look contingent, the constants look arbitrary, the landscape looks real. And if it is real, then asking why the laws of physics are what they are is like asking why the weather in Istanbul is what it is today. There's an explanation, but it's historical and contingent, not fundamental and necessary. Let me take this in another direction because there's something even more radical lurking here. The question of whether the laws of physics change over time. You might assume the answer is obviously no. The whole point of a law is that it's permanent. Gravity worked the same way a billion years ago as it does today. The speed of light hasn't changed, the charge of the electron is constant, and as far as we can tell, this is correct. The laws appear to be the same everywhere in the observable universe, and at every time we've been able to probe. The light from distant galaxies, light that left billions of years ago, shows the same spectral lines we see in laboratories on Earth, the same physics at work, the same constants in play. But appearances can be deceiving. There are theories that predict the constants of nature might change very slowly over cosmic time. Not quickly enough for us to notice in a human lifetime, or even in the lifetime of a civilization, but over billions of years, the fine structure constant might drift. The gravitational constant might shift. The laws might not be permanent at all. They might be evolving. In 1937, the great physicist Paul Dirac proposed exactly this. He noticed some curious numerical coincidences between very large numbers in physics and cosmology and suggested that the gravitational constant might decrease with time. His specific idea turned out to be wrong, or at least not supported by observation, but the general possibility remains open. We've constrained how fast the constants can change. We know the fine structure constant hasn't changed by more than about 1 part in 100,000 over the last 10 billion years. That's impressively stable, but it's not zero change. And some observations, controversial observations, suggest that the fine structure constant might actually vary slightly in different directions in the sky. If confirmed, this would be revolutionary. It would mean that what we call the laws of physics are not even uniform across space, let alone permanent across time. They would be more like the weather, varying from place to place and time to time, governed by deeper dynamics we don't yet understand. Now, even if the constants don't change, there's another sense in which the laws of physics are not permanent. Phase transitions. You know what a phase transition is? Water freezes into ice. Water boils into steam. The properties of the material change dramatically at specific temperatures. The laws governing ice are different from the laws governing liquid water, are different from the laws governing steam. Not fundamentally different. They all follow from the same underlying quantum mechanics. But the effective laws, the rules that describe what you actually observe, are completely different in each phase. Something similar may have happened to the universe. In the very early universe, in the first fractions of a second after the Big Bang, the universe was at incredibly high temperatures, so high that the fundamental forces of nature, electromagnetism, the weak nuclear force, the strong nuclear force, may have been unified into a single force. As the universe cooled, these forces separated, they underwent phase transitions. The unified force broke apart into the distinct forces we observe today, each with its own strength and its own rules. Before those phase transitions, the laws of physics were different, not slightly different, fundamentally different. The particles we know didn't exist in their current forms. The forces we observe hadn't yet separated. The rules of the game were completely different. So the laws of physics as we know them, the standard model, general relativity, all of it, these aren't eternal truths. They're the result of a cooling process. They're what emerged after the universe underwent a series of phase transitions in its first moments. Before those transitions, different laws applied. And in principle, if you could heat the universe back up to those extreme temperatures, the current laws would dissolve back into something more fundamental. The laws are frozen accidents. The particular pattern that crystallized out of the hot early universe as it cooled, like the specific shape of a snowflake determined by the conditions during its formation, not by some eternal snowflake law. This is not speculation. We have strong evidence for at least one such phase transition, the electro-weak phase transition, where the electromagnetic force and the weak nuclear force separated. This happened about a trillionth of a second after the Big Bang, at a temperature of about 100 billion degrees. Before this transition, photons and W and Z bosons were all the same thing. After it, they became distinct particles with different masses and different behaviors. The law changed, not the deep underlying law, if there is one, but the effective law. The law that describes what you actually see and measure. And this is what I mean when I say the laws of physics are not laws, they're effective descriptions. They describe what happens in our particular universe, at our particular temperatures, at our particular energy scales, change the conditions, and the laws change with them. Now, here's where I want to connect all of this to something deeply philosophical, the relationship between mathematics and reality. Most physicists are, whether they admit it or not, mathematical Platonists. They believe that mathematical structures exist independently of the physical universe, that the equations of physics describe a pre-existing mathematical reality, that the universe is in some deep sense mathematical. I used to believe this. I'm not so sure anymore. Here's why. If the laws of physics are approximations, if they change with conditions, if they're contingent rather than necessary, then the mathematical structures we use to describe them aren't discoveries about the nature of reality. They're inventions, tools, maps. And a map is not the territory. Think about Newtonian gravity. For 200 years, physicists believed Newton's equations described the actual mechanism of gravity. They believed there was literally a force reaching across empty space, pulling objects together. Then Einstein came along and showed that this picture was wrong. There's no force, there's curved space-time, and objects follow the straightest possible paths through that curved geometry. The mathematics changed, the picture changed, the understanding changed. What didn't change was the phenomena. Apples still fall. Planets still orbit. The universe doesn't care which mathematical framework we use to describe it. The universe just does what it does. We invent stories, mathematical stories, to describe what it does. Some stories work better than others. Some work in certain domains and fail in others, but they're all stories, now you might say. But Lenny, the mathematical stories make predictions, incredibly precise predictions, predictions that have been confirmed to 12 decimal places. Doesn't that mean the math is real? And I understand the argument, but consider this. A medieval monk might have said the same thing about his cosmological model. The Earth is at the center. The planets move on crystal spheres. The model predicted planetary positions reasonably well. Did that make crystal spheres real? Obviously not. Prediction is not the same as truth. A model can predict beautifully and still be completely wrong about the underlying mechanism. Our current models might be in exactly that situation. They predict, they calculate, they work, but the picture they paint of reality might be as wrong as crystal spheres. And there's an even deeper problem: Gödel's incompleteness theorems. In 1931, Kurt Gödel proved that any sufficiently powerful mathematical system contains true statements that cannot be proven within that system. Mathematics is inherently incomplete. It cannot fully describe itself. If the universe is truly mathematical, then Gödel's theorem implies that no mathematical theory can fully describe the universe. There will always be truths about reality that our equations cannot capture. The laws of physics as mathematical structures are necessarily incomplete descriptions of reality, not just because we haven't found the right equations yet, but because no set of equations can be complete. This is a fundamental limitation of mathematics itself. And it means that the dream of a final theory, a theory of everything, a single set of equations that describes all of reality with perfect accuracy, might be not just difficult, but impossible. Not because we're not smart enough, because mathematics isn't powerful enough. Now, let me talk about something that I find both humbling and fascinating. The role of observation in defining what we call laws. We discover laws by observing patterns. We watch the universe, we see regularities, we describe those regularities mathematically, and we call the result a law. But here's the thing. We can only observe a tiny fraction of the universe. We can only see out to the cosmological horizon about 46 billion light years in every direction. Beyond that, light hasn't had time to reach us since the Big Bang. We have no information about what lies beyond, and we can only observe a limited range of energies. Our particle accelerators reach energies of about 10 trillion electron volts. The Planck energy, where quantum gravity effects become important, is about a quadrillion times higher. We've never probed anything close to those energies, and we probably never will. So the laws of physics we've discovered are laws about the observable universe at accessible energies. They might be completely different in regions we can't see or at energies we can't reach. We have no way of knowing. We extrapolate. We assume the laws are the same everywhere. We call this the cosmological principle, but it's an assumption, a useful assumption, a necessary assumption for making progress, but an assumption nonetheless. Imagine an ant living on a beach. The ant observes that the ground is made of sand. Everywhere the ant looks sand. The ant formulates a law. The ground is made of sand. The law works perfectly within the ant's experience, but the ant has never been to a mountain or a forest or an ocean. The ant's law is a description of its local environment, not a universal truth. We might be that ant. Our laws might be descriptions of our local patch of reality. True here, maybe not true there. True now, maybe not true then. True at our energies, maybe not true at other energies. And we would have no way of knowing the difference. Let me bring this back to something practical, because I don't want you to think this is all just philosophical hand-waving. The fact that the laws of physics are not laws in the absolute sense has real consequences for how we do science. It means we should always be looking for anomalies, for places where the laws break down, because those are the places where deeper physics is hiding. The ultraviolet catastrophe, the failure of classical physics to describe black-body radiation, led to quantum mechanics. The failure of Newtonian gravity to account for Mercury's orbital precession led to general relativity. The failure of the Standard Model to account for neutrino masses, dark matter, dark energy, the matter-antimatter asymmetry. These failures are not embarrassments, they're clues. They're telling us that our current laws are approximations and that something deeper is waiting to be discovered. Every failure of a law is a gift. It's the universe whispering that you haven't got it right yet, that there's more to learn, that the real rules, if there are real rules, are still hidden beneath the surface. And this is what makes physics endlessly exciting to me. Even after 50 years, we're not done. We're not close to done. Every theory we've built, no matter how successful, no matter how beautiful, no matter how precisely confirmed, is provisional, temporary, an approximation waiting to be replaced. Some of my colleagues find this depressing. They want certainty. They want final answers. They want the book of nature to have a last page. But I find it exhilarating. It means the universe is deeper than we thought, more subtle, more surprising, more resistant to our attempts to capture it in neat equations. The laws of physics are not laws. They're our best current stories about a universe that is far stranger, far more complex, and far more mysterious than any story we've yet told. And the next story, whatever it turns out to be, will also not be the final one, because the universe doesn't owe us a final answer. It doesn't owe us neat equations or beautiful theories or elegant mathematics. It owes us nothing. It just is. And all we can do is keep watching, keep thinking, keep building better approximations, and keep being honest about what we know and what we don't. That's what science is, not a collection of laws. Not a book of eternal truths, but a process. An endless, humbling, magnificent process of getting less wrong about a universe that will always be more than we can describe. So the next time someone tells you that the laws of physics say this, or the laws of physics forbid that, remember what I've told you. Those aren't laws, they're descriptions. Provisional, approximate, contingent descriptions of a universe we barely understand. They work. They work spectacularly well within their domains. But they're not the truth. They're our best current attempt at the truth, and the truth, whatever it is still out there waiting to surprise us, waiting to overturn everything we think we know. Again, just as it has every single time before. That's the real lesson of physics. Not that we've discovered the rules, but that every time we think we've discovered the rules, the universe shows us we were wrong. And that process, that beautiful, frustrating, never-ending process of being wrong and learning from it, that's the closest thing to a law of physics I know. Thank you for listening. And remember, the next time you look at the equations in a physics textbook, you're not looking at the rules of the universe. You're looking at humanity's best guess. And it is, I promise you, not the last guess we'll make.